excited to get started with our second day of this workshop. Before we get started, I'd like to remind everyone again to submit a talk for the lightning session on Friday. If you have any submissions, please send them to Nico, myself, or Nicola. And with that, let's get started. We're very excited to have this morning Jeongwan Haah talk about what it means to have a logical qubit.
Thank you. Thank you for being here in the early morning, and I thank the organizers for having me an hour, when I requested only 30 minutes. So this is an unusual talk for me because there's no paper that I cite that is written by me or other close friends with. So I'm gonna cite everyone else's. So yeah, what is your logical qubit? Maybe this is a time for you to think about the question, and that's all I ask of you. Let me guide you through that question. I'm not going to give you an answer, by the way. I promise. So we want logical qubits. Why? Because long quantum computation will require good qubits and good operations. There's no doubt about that. And the existing technologies doesn't quite meet the bar. There's too much noise, and it is well still explored, but it's hard to find a useful application. So there are some already interesting experiments going on. You can sample from some distribution, which is argued to be hard in the classical manner, and you can implement some interesting condensed matter systems in a small scale. And well, eventually with the logical qubits, we would like to, for example, factor large integers or estimate the ground state energy, which applies for the quantum chemistry problems. And well, maybe we can do it may be a great tool for doing the quantum physics, probing quantum dynamics or simulating materials. Maybe we could try some models of AI, let alone, the theoretical guarantees. Let me ask you, we all have a classical computer. Do you think you have a Turing machine? Well, theoretically speaking, no, because Turing machine is a mathematical ideal, but in all practical manner, you probably say yes. But why? Why do you say that? Maybe, because you've seen overwhelming evidence. Your laptop is doing some very non-trivial calculation for growing sizes, and you can believe in your asymptotics of your numerics. And those results are very reliable. It is cross-checked over many machines, and it gives us consistent results. You don't really doubt anything about your machine other than some sporadic failures of hardware, which happens in high-performance computing. But other than that, it's pretty good. It's a very good approximation to the Turing machine. And we want the same in the quantum regime. And the demonstration of a logical qubit should be the path forward to that goal. So probably we would want that the logical error rate is smaller than the physical error rate. And probably we would want that we want to see examples of some scalable family, because your one demonstration will not prove or give us sufficient belief that it is now going to be a very useful quantum machine. We need some, we need to build up our belief. And for that matter, we probably want to implement, here's my future plan, and here's the infinite family of codes, and we're gonna implement like the first two instances. That's probably what we're gonna do. And likely, we would want to error correct rather than detect and post-select. Why? Because this is going to work at any scale in principle. The latter will not work in principle because it will take exponentially many samples to get any meaningful results. And first and foremost, we would want to see the universal gate set to do arbitrary quantum computation. That's pretty much what we want to see. We will come back to these points later. There are many caveats. And because we are building a computer, we want to see some problem solving is done with your computer too. But it becomes really tricky at the current situation, because it's inherently apples to oranges. With the physical qubits, what you want to do? Probably you will implement some unitary CZ gates, which is physically most relevant. Typically, the two levels that you choose for your physical qubit is the lowest energy level, and the phase gate is the most naturally induced operation. And in many platforms, we can do the single qubit arbitrary rotation, and probably we're going to measure in some fixed spaces. But we will probably never going to do with the physical qubits that you want to initialize the qubit over and over again on a fixed state, other than testing purpose. Why would you do that in an algorithm when you can do the unitary directly? And probably we're not going to implement the measuring like a weight 2 operator on a physical qubit. Is there any natural platform that does the job? I don't know. Maybe there is, but it's not immediate for me. On the other hand, if you're proposing to build a quantum computer using, say, the surface code architecture, then it is unlikely that you will ever do C0 unitary gate. And you will probably always do via some lattice surgery operation, measuring the 2-qubit Pauli operator. And maybe you can also measure some mixed ones and do some Hadamard. And to achieve the universality, you will be injecting your T states. That's pretty much all you're going to do. Now, how can I compare this to that? But even theoretically, well, I mean, at the simulation level, it becomes tricky because, say, you have invented a code with a large number of encoded qubits. What are you going to do with it? Probably, likely, because you have many qubits, your logical qubit, well, labeling logical qubit 1 depends up to you. I mean, choice of a logical operator is up to you. So likely that you would want to avoid any Clifford operation altogether. The operations that was important at the physical level or at the surface code level just becomes cost 0. The remaining cost is now in toast to other operation, for example, measuring some product of 2 logical operators, or maybe injecting T. How would you compare this? And many people say, oh, we got 10 logical qubits, 20 logical qubits, whatever. But if I must need 2 code patches to implement 1 unitary operation, did I make 2 logical qubits or 1? Even counting is ambiguous in this situation when you change the targeting qubit. But scale matters. If you give me a ton of apples or a ton of oranges, then probably that's more useful than just 3 apples. That's for sure. And that's the regime we would want. But we're not yet there yet, and the comparison becomes very tricky. Now, okay, so let's go into what has been done. Well, this is by no means any representative of the experiments, but I somehow randomly chose ones. The first question, does quantum error correction ever work? Okay, let's test that. On the people around 2020 have implemented this 9-qubit code, and they have implemented syndrome extraction, whose correction is deferred to the end. And they measure the logical eigenvalue upon initialization of some logical qubit. And
sorry,
yes.
it's going to be a pain. But this is really like a Duke Maryland result.
Oh.
Like it's not the company.
Oh.
Like Chris List is made of me.
Okay.
But, sorry. Steve, that was just a comment. I just wanted to say.
Oh, yes. Apologies. My sincere apologies. Yeah, so and they have found that some initial states are more fiducial than when it is encoded than whether that is unencoded. So in that regard, QEC works. Okay, that's great. Some other experiments they have looked at the NV centers in the diamond, and they implement even smaller code. And well, the more advanced point in this experiment is that they have implemented the full Clifford operations on a single qubit. It's a 5-qubit code. With a permutation, you can do that. And they compare the two versions of the step preparation. One is using the one fault tolerant circuit. The other is non-fault tolerant circuit. And the fault tolerant circuit does the job. Okay, great. Later on, now, well, we got two patches, two code blocks, and they teleport the T state into the other qubit. And it works as expected. And well, as far as I can tell, this experiment is not a comparison of anything else. It's just a demonstration of that there is a universal case set that one can do. Okay, that's right. So this question, does QC ever work? That question seems to check out. Now, the next question, can we make it better? Well, the question of being better is a bit problematic, but still we can do. There was a paper from Continuum where the affiliation back then was Honeywell, but later changed on Continuum. They implement this eigenstates on this Steam code, and then implemented syndrome extraction cycles, and they measure the state preparation and measurements. That's what SPAM stands for. And physical SPAM error rate is higher than the logical SPAM error rate. Okay, that sounds something. Something we have made a genuine progress, because this is what we would have without any error correction. This is what we achieved with error correction. Okay, that's great. That's what we wanted to do. But they noted a phrase which I liked. Let me read it aloud. A complete understanding of overhead associated with the quantum error correction will have to wait until logical qubit entangling operations are characterized. Here, only single qubit is there. And this remark is important in the sense that what does it mean to have a single logical qubit when it's never going to interact with anything else? It's like a human on an outer space. Where's my society? 1 year later, they improved their hardware, and now they've done something more sophisticated. They prepare the two blocks of the Steam code, and then they state preparation in the fault tolerant way, and they do the transfers of CNOT gate, and so they are creating a Bell pair at the logical level, and then measure the fidelity of the Bell state. Now, when you measure the fidelity, it does not mean the literal quantum state's fidelity level. In operational sense, you do the tomography by measuring somehow Pauli operator on the logical level, and then reverse and infer the fidelity of the Bell pair. And they reported a better number at the logical level than the physical level. Okay, that's great. We have made some non-trivial state on the logical level. But for me, as a theorist, the biggest lesson, okay, the noise physics that we proposed in the study of error correction seems to be relevant. It's a local independent, and the experimental result matches with our expectation. Okay, and the ion manipulation technology is pretty good. Now there's another experiment, but I thought I would have one slide just to explain a different category of codes. I knew there was experts in this audience better than I am, but there is something called bosonic codes, which is very different from the usual Pauli stabilizer code. You begin with the infinite dimensional Hilbert space, whose basis is labeled by the photon number. It's a truly infinite dimensional. And you consider the eigenstates of the various operators acting on this infinite Hilbert space, and you take a certain superposition to make a code. And the well-studied codes are named like the CAD codes or GKP, Gottesman, Kitaev, and Prescott codes. And binomial codes are there. And some of the code states have been implemented in the lab, which I'll come back in a moment. And the biggest comparison between the Pauli stabilizer qubit code versus this boson code is that you get the redundancy from having many qubits in the usual setting. Here, it's already large space. So you need to find the well-defined two-dimensional subspace, and that's all you do. The code family in this case is a sequence of many instances, but the code family in this case will be a sequence of different choices of two-dimensional hyperspace. Okay. And yes, using those bosonic code, there have been impressive experiments where they made this calc code using superposing two coherent states. And the dominant error in this case is errors that pushes everything to the vacuum. So it loses the photons to the environment. Right. And they have reported the coherence time gain of 1.1 over best physical qubit back then by using this encoding. Okay. Oh, my logical qubit lived longer. How awesome that is. A few years later, even bigger coherence time gain is reported. Now it's almost 2 times as long than the physical qubit. This is just for last year. They have said that some shortcoming of the previous experiment is now overcome. That in this experiment, the co-states are too much pushed to the origin. The loss was too big, but now that problem appears to be corrected. Correct me if I'm making incorrect statements, but that's what I read. But now this is a lifetime. Clifford operations on the bosonic codes are known to be possible by some Gaussian quantum optic operations, but those operations were not reported in those papers. So the main question in this line of work, how do logical operations improve? That's the main question. But at the same time, I urge you to think about this question. Is the longevity of a logical qubit necessary? Or is it sufficient? Any vote?
Neither.
Right. Neither. Why? Let me make a joke. If I give you a drink that makes you live 300 years, oh, that's awesome. That's a revolutionary in the human medicine. Fine print, there is. All humans must take it. Otherwise, it doesn't work. And your activity will slow down by a factor of 10. You're laughing, you're blinking, you're walking, you're writing, and you're thinking. Everything just slows down. Would you take it? Another episode. Here's a system admin, and this admin comes to a manager and complains that, oh, this server burns out every year. This is too expensive to replace. What should I do? Okay, the manager says, oh, okay, then make it slower. And it will last longer. What? But our revenue is the number of operations. Excuse me, you can't do that. Well, then make it faster and burn it faster. Okay, that's great. All right. So the main focus should be on a more operational task. So people have demonstrated this computational tasks. And, this paper demonstrated 1-bit adder, which is basically just one CCZ gate up to a few Clifford operations. And they used the A32 code that converts the transversal T into the CCZ gate. And it's an error detection code, of course. And then later paper achieved a similar thing. They have done some more complicated operations, more zoo of, the various operations at the logical level, and they have seen the improvements. Okay, that's good. Some operations gets better. And more recently, like a couple of months ago, more impressive experimental reports came along that they had 16 patches of that qubits, and they have implemented a whole bunch of logical qubit. And they have reported some sampling tasks, and it seems that it's performing well. But in all cases, the code used is an error detection. And of course, it is post-selected upon successful syndrome measurements. Can we call that as improvement? That's up to you. I'm not going to answer. Just posing a question. And more important claims came, I think, we have seen claims. Larger codes works better. Okay, that's why do we want that? I alerted in the beginning that we want to see the future. We want to build up the belief on the quantum error correction at a scalable, useful quantum computer. And for that purpose, we have to show the trend that error rate's going down. Okay, so this is an important piece that we have to demonstrate. And as far as I can tell, there's only 2 experiments in this regard, and that they all use the surface code. If you know other experiments, let me know. But now, since we're talking about the scaling, I have to mention the threshold theorem, because it is ultimately based on the threshold theorem. If you can do it, well, here's a statement. There exists a local noise model. I put it up there because this is not often explicitly mentioned, but the statement depends on your noise model. So there is a noise model parameterized by a real number epsilon and some positive number epsilon 0, which we call threshold value, such that if your epsilon is smaller than that threshold value, then you can do any quantum circuit of size is efficiently mapped to noisy circuit of slightly blow up size, but not too much, controlled by a modest performing classical computer, but error-free. We don't worry about error, such that the output distribution is similar to what is designed. That's the threshold. You have to specify a noise model. Otherwise, the statement is incomplete. Nonetheless, we speak about threshold value without referring to the noise model, based on the belief that some reasonable set of noise models are comparable, which you should ask yourself. And there's a similar word called pseudo-threshold. And pseudo-threshold is defined to be an error rate P of a physical qubit operation, such that for a certain error correction scheme, the logical error rate is also P. So below that P value, things get improved. There are prerequisites, however. All noise has to be parameterized by one real number P. Is that a reasonable thing to do? If you're doing experiments, there are like 15 parameters in your noise error budget. And when you can work on one error parameter to reduce it, while other things may go up. What did I do? How can I parameterize it? Should I just scale them all together by some common scalar P? Is that a reasonable thing to do? I don't know, maybe. And most importantly, the notion of logical error rate must be defined. And that's not trivial. What do I mean by logical error rate? The threshold theorem does not define logical error rate for you. It is something you have to come up. It is a proxy to infer that the final logical outcome is close to the ideal one. It's an intermediate gadget. But somehow, while we're studying this intermediate gadget or notion became the dominant player in the scene. But a priori, this is something you have to define. And it's not always trivial. And another condition to talk about pseudo-threshold is that there is a functional relation. It's probably true, and for all examples I know, it is true. But is it always true? Yeah. I mean, is it always a monotonic function? I don't know. Now, people talk about threshold for identity gates and CNOTs. Does that really make sense? Let me recall the threshold theorem again. There exists a noise model by epsilon such that any quantum circuit can now be mapped to a noisy quantum circuit. That's the context we talk about the threshold. If you remove this condition of any quantum circuit to a circuit consisting of identity and CNOTs, then what do we get? We don't need any condition on epsilon because the threshold theorem only says that there's an efficient mapping to the noise circuit. And while you're computing the efficient mapping, you can just finish your calculation because the C naught or identity is not universal. So threshold for C naught, as it is formally infinity. Because you don't ever have to work with hardware. And what do you mean by threshold for C naught or identity? Nonetheless, right? Nonetheless, we say that, oh, the threshold of the toric code or surface code as a quantum memory, the identity gate, is around 1%. Why do we say that? It is because we have studied that particular example so much that when we look at the logical circuit composed of some surgery operation, for example, then we know how the overall overall error rate will be, and it's simple function or simple relation with the examination, something happening at the logical block that appears to implement the identity gate. And we extrapolate that knowledge to the arbitrary gate set. And this is the basis we talk about, oh, the threshold for the surface code is around 1%. And yeah, anyone who worked on the surface code architecture will understand what I mean here. Here is some logical gadgets that will implement the universal gate set, quoted from this paper. And most of the things are happening, almost all of the operations that is happening in this logical circuit is identical to the quantum memory situation.
So maybe I just disagree with the previous slide. Like you say the threshold is infinite.
Yeah.
I see your point.
Yeah.
Like you're not wrong, but somehow I feel like this mischaracterizes what's happening when we talk about.
Yeah. So I mean, all I'm saying is, well, I mean, that plain statement is meaningless, but it becomes meaningful because we understand what's going on at the logical level. Because we understand what's going on at the logical operation level, at least order of magnitude. And because of that base, we can talk we can talk about the threshold for identity or CNOS or any Qubit operation. It requires meaning because we are our understanding.
Right, but it feels like from the previous slide, you're sort of you're giving an imprecise, because this is a talk,
Yeah.
but it's a theorem statement.
Uh-huh.
And you're showing, well, if I take this theorem statement about universal quantum computation and I restrict it to memory, then the result is meaningless. I don't get a meaningful number. But it seems like on this slide, you're saying that there isn't a precise definition of memory threshold. And I think that there probably is, although I agree with your point that it would need to be modified relative to the definition of universal quantum computation threshold.
Yeah.
So maybe you agree with that and there's no issue. Okay.
And we also say that some quantum codes idling performance, however it is defined, is a good proxy for anything else. If you think about that sentence only, it doesn't make sense. Idling performance. What do you mean? So, over the course of 20 years or something, I think this is what happened. Some new code is invented. Some error correcting code is proposed without ever worrying too much about the logical operation side. And then there's some follow-up work that justifies that the previous work didn't have to consider that too seriously. There's no too big a discrepancy. Sometimes this too happens in the same paper, sometimes not. And that's what's happening. And when you write the first one only without this worrying about the second part, then you're implicit about, oh, later someone will come up with the operational meaning to my code. That's an underlying implicit assumption I read in the literature. Now, okay, let's get back to the experimental reports. There was exciting announcement from Google a couple of years ago, well, a year and a half ago. They implemented surface code and tens of syndrome extraction cycles they have literally implemented, which is very impressive. And then they have reported error rates per syndrome extraction cycle. The T is the actual time, with being the around 3% at the distance 3 and a slightly smaller number at distance 5. Oh, we have seen the scaling. That sounds great. But, and they have acknowledged, however, that this situation is not likely under threshold, it's over threshold. So even if you fix all the assumptions about the physical qubit and you just increase the system size, then the error rate will actually go up. They have tested it in using simulation, and they have acknowledged that. But let's read these numbers more carefully. It is error rate per syndrome extraction cycle. And we all know that the surface code-based architecture has logical unit time that is proportional to the code distance times the one round of syndrome extraction. Now, so the logical clock cycle is now increased by a factor of 5/3. And if you take that into account, the logical conclusion from their reporting number is that we can run a shorter quantum algorithms with a larger code. Do you call that improvement? Have we suppressed the errors? What have we done? And a couple of months, 2 months ago, very impressive experimental setup from Harvard, Quera, Maryland, and MIT group have implemented this reconfigurable, where's the accent? Reconfigurable. Neutral atoms, and they got a ton of atoms, they got a ton of qubits, and they can address individual qubits, which is marvelous. They can rearrange, shuffle them around, they let them interact when they want. They can to the storage region, and then they can read out by flying their atoms away. Very good. The sheer scale is very impressive. And I got excited too. And many people are excited about it too. Right. And since they got so many qubits, they can now implement tens of code patches, which is unprecedented. And then they have shown several demos. It's a library of demos in one paper. They have 4 of them. One is that they have shown that the logical CNOT is improving with code distance. And then they also implemented some non-trivial state on the 4 logical qubits. And they have shown the sampling experiment using more complicated codes. And they even measure like an entanglement entropy for some subsystems. It's a gigantic paper. As this is a quantum error correction workshop, I want to focus on this. See, not improving with the code distance. The technical point on this experiment is using the surface code. All the other is using the error detecting mode. All the other is operated under the error detecting mode to some varying degree. Which is fine. I mean, there's nothing wrong with the post-selection. Right. So in that first demonstration, what they have done is the following. They prepared product state with physical qubits. They initialized it. And then they implemented the 1 round of surface code syndrome measurement, just measuring the weight 4 Pauli operator. And then they implemented transfer CNOT. There's no 2-dimensional connectivity constraint. They can literally move the atoms to overlay, right? Like here. And then they shine some laser to induce the interaction among the qubits to induce the CNOT gate. And they measure out. And then based on the measurement outcome, they decode the error correct. And then they report the corrected values of logical product, the XX and ZZ. This is what's been done. And they have seen very promising results. One, they decode individual patches separately. There's no shared information between the two code patches. And they have seen the increase in the error rate. Yeah, this is like a 20%, this is 40%. It's increasing. But once they combine the measurement outcomes from the both parties using the syntrom information only, not the logical information to infer the logical qubit, but only the syntrom information, they have seen the decrease in the error rate. This is around 10%, this is around 7%. Okay, so, and just the fact that distance 3, 5, and 7, the 3 instances are implemented is the state of art. Now let's look at this scaling a little bit closer. And they have claimed that, we have seen the sub-threshold for C0. And they have, they claimed, this is a genuine performance improvement for the entangling operations for encoded qubits. Okay. Now, let's review. Why do we ever need that many rounds of syntrom extraction in the surface code when that experiment just implemented just once? Let's examine what goes wrong what goes wrong or good if you do it too short. Why do we need D rounds? All because of the measurement outcome you don't believe. And when in doubt, ask many times. So you repeat your measurement to boost your confidence, and that's the underlying logic that you have to repeat. But there is we can make it sharper. So let me take a very simple example. So there's no, just a teleportation. Some plus state is prepared, arbitrary state is known. We make a measurement of Pauli product, ZZ, and then based on the outcome, you apply certain Pauli correction, and you measure out this qubit where the original qubit was here in some X basis, and based on the outcome, you apply another Pauli correction, and the result is genuinely teleported. If this measurement outcome is wrong, then incorrect Pauli correction will be applied, and the teleportation fails. So even if you don't assume any error on your physical qubit, if you only impose the error on the measurement outcome, then still it has an operational consequence that in this example, the teleportation fails. So your reading, the fiduciality of your reading becomes a genuine thing. It's not just a subjective notion. Measurement fidelity is the state's fidelity. Now, let's make a thought experiment. I want to make a cast state. How do I do that? Protocol is that I prepare every qubit in the plus state at the eigenstate of X, and then I measure the Ising couplings, ZZ on the nearest neighbor. That's the only source of that's the only source of error in this thought experiment. And then, depending on the measurement outcome, you apply a correction operator to make a genuine cast state. And since the underlying state was an eigenstate of all X operator acting everywhere, which correction doesn't matter. I could have applied the correction from Pauli string that starts from the left or Pauli string that starts from the right, but it doesn't matter. Okay, that's the correct protocol to prepare a cast state under the assumption. Now, suppose I made a mistake in the measurement outcome reading. Then, because of the protocol, I have to apply those X operators. Okay, so one mistake resulting in a long string of X's. That's the best I can do. But because of that, what you can prove is the following. The underlying state after this protocol in the presence of this noise is actually close to a product state rather than a cast state. So for any parameter L, there is an incoherent mixture of the tensor product state such that their trace distance is small that much. For a fixed P, for a large L, this is asymptotically vanishing. So it is approaching the product state. And you can choose L to be only that much. Some constant times log in the system size. Yeah, you intended to prepare a cast state, but you end up preparing product state because you only have measured once. Just a simple piece of graph. But if you repeat your measurement sufficiently many times, then by doing the majority vote, you can avoid this catastrophe. Okay, well, that was a thought experiment. Is there an operational consequence? Yes, there is. Well, again, suppose error may occur only in the measurement outcome, nothing else. Everything else is perfect. Now, I'm going to use repetition code, the same protocol, but this time I'm going to do the logical teleportation. So I have some arbitrary encoded state on the left, and I prepare an ancillary state on the right by doing the protocol as before. Product state, measure the ZZ coupling once, and I do the X correction based on the measurement outcome. And that's my preparation of the ancillary system. And I do this transfers of C naught and measure at the left, and my logical qubit will be teleported to the right. But because of the previous analysis, this state is close to a product state rather than a cast state. So if you make a mistake on the measurement here, there will be a long string of X inserted, which will be propagated to the left by the transfers of C naught, and your measurement, the destructive measurement on the left will be wrong. And the probability of that happening is order P. There is no impact from the large code distance. Therefore, the teleportation fails with probability order P. There's no way around. But if you're going to measure the barrel correlation, you will never know. Again, the same error model. Only measurements could be wrong. Everything else is correct. And instead of bringing unknown encoded state, just prepare a zero state, and then try to make a logical Bell pair and try make a logical make a destructive measurement to infer the logical values. Long X errors may be propagated here, but if you are looking at the logical XX, those kind of errors doesn't matter. They commute with the measurement. If you're measuring the logical ZZ, the same error will appear on both sides. So you never know. You will never encounter any error in your protocol in this Bell measurement when logical teleportation will fail with probability order P. Okay, let me just recap. Toy model, noise on the measurement only, measuring stabilizer once on the repetition code. It fails to generate the fiducial cast state. Hence, it fails to teleport unknown states, but it may produce genuine Bell correlation. And the same math, virtually the same math, applies for the two-dimensional toric code in the presence of qubit noise. Hardly anything changes. Even the formula looks exactly the same. You are intended to prepare the toric surface code state, but you end up preparing actually a product state in the large code distance limit. Your logical teleportation will fail with a probability P, but that failure will never be seen in the logical Bell correlation report. But in the actual experiment, the noise exists because the absence of error in the Bell correlation measurement was only assuming the measurement errors. If you have other errors, then there's a chance that even that fails. Okay, but despite this, this paper claims that, we have improved entangling gates with the code distance. Okay, so now here's a question. Is this scaling demo a gadget that can be used for general quantum circuit? It's a yes or no question. If yes, I would call it breakthrough. I mean, surface code architecture has been studied for decades, and the logical cycle time is order D. That has been around as a fact for many years. Now, maybe we can reduce that to order 1. If answer to this question is yes. If no, then what are we doing here? Okay, here's my some summary thoughts in the logical qubit demos. Yes, we want logical error rate to be much smaller than the physical error rate, but it's an apples to oranges comparison. It's really hard to say one is better, but a ton of apple or a ton of oranges is better than a few. So scaling, or the difference in scale matters. We might want to implement instance of some infinite family, but this is a real life, and infinite is a mathematical ideal. We don't need that. It suffices to show the trend, whatever code family you choose or whatever instance you choose. I wouldn't care. And this scaling experiment is completely unnecessary if you reach already a very good fidelity. And probably, likely, we will want error correct rather than detect and post-select, because detect and post-select is believed to have too small success probability. But if that small probability solves your problem, you must do. Please do. We always do. Research is like that. We want to see a universal set of logical components, and that's the first and the last point of any logical qubit. It's very demanding, I understand, especially because different components in your logical demonstration may have a very poorly defined time boundary conditions. Think about the surface code. How do you put the time boundary for a component? And you have to ask yourself, is that time component will be a good proxy for the situation where this component is working in the presence of all the other gates? Probably yes, but you need to be careful. And as we have seen in examples, please don't optimize components too prematurely. It may lead to a situation where your demonstrated component will not fit anywhere. Okay, well, undoubtedly, this is a very exciting time for quantum information science. We got multiple experimental platforms. There's a new design. There is a new code. That's the purpose where we're getting here. And so far, the QEC demos have shown consistency with the simulation results, which corroborates with the fact that the locality that we assume in the analysis is actually really close to the truth. And I ask that people should pay more attention to the operational meaning. An error rate epsilon at the physical or at the logical level must mean that you can do 1/epsilon order times operations. It can only be order 1/epsilon. There's no universal constant because it's an apple to oranges comparison, but it must carry that meaning. And when you ever want to claim a break-even instance, it's extremely delicate because you want to stick on some task that is well-defined, well-motivated, and that task has to improve. So rather than saying by QEC we realize this many logical qubits, I ask you to say by QEC we can do this and that, more or better. That's what we should aim for. Yeah, thanks for the time.
Thank you for the fantastic talk. Are there any questions?
Okay. So I have 2 questions if you'll indulge me. So the first is, we know for many systems, the physical qubits have an error of, say, near 10 to the minus 3 now. So, like, just doing 1,000 operations on one qubit is no interest, right? So maybe want to do hundreds of operations on tens of qubits. And of course, that it's going to take a long time. So this, I don't know, I feel like this strike, so what do you see as the intermediate goal for the strikeout line? Like, I want people to work on error correction. I don't want them not to do it until it's better. Then none of us will get anywhere. So what's a good intermediate goal?
Well, my main motivation to give this kind of talk is that I see some inflated claims, and I don't want that. It's harmful for the community. We can do the rigorous science without inflating the words. That way, we would gain more respect.
And my second question
Yes.
is, so, if you do like Steen or Knill style error correction, you can just do everything in one. You don't have to worry about a T.
Right.
And then I don't know the details of their like experimental error model, but it seems like the probability of measurements failing can be low enough, right? Because in the end, the e to the minus PL depends on P.
Yes. Oh, yes. Right. So there's a mismatch between what I said and versus the scale we're talking about. If the P is like a 10 to the minus 3 and you're working with a tens of qubits, 1 over P is pretty large. And maybe that's good enough for whatever purpose you are doing. I imagine that any improvement claim must come after you have seen, well, I mean, the consensus on the improvement will appear after we have seen many aspects of the demo. It's not going to be just a single demonstration. Oh, here's the thing, and this is the answer. Same thing happens in all of science, I think, and especially so in this area too. Yes, Steen error questioning, Knill error question, they're great. If we can show something can be done, I don't know if there's any report along that direction. We don't have much in.
Thanks for the talk, Jeongwan. I was maybe a little confused by one of the things you said about not having constant time operations. Do you not think that in the surface code, if you have long-range operations allowed, then having a mix of logical operations, some of which are order D depth, and others like the C naught, if that first C naught would be order 1.
Right.
So you do agree that that should be fine.
Oh yeah.
And then the query experiment, I haven't read carefully through the paper, but I guess that they were claiming that they were analyzing a transverse C naught, which is order 1 depth in that sense. Are you complaining that is that different from? I see Shruti shaking your head, so I'm wondering maybe you could answer this.
But and then I just want to comment on Michael's. I mean, it is the Harvard students really did it, so people shouldn't call it the queer experiment. Right, queer.
So
some great theory work from MIT and Maryland.
well, yeah. So I that's why I asked you a question. Does this demonstration an indication of a gadget that can be used in general purpose circuit?
Like to do a like in a algorithm, if you want to do a CMOS somewhere, you need D rounds of syndrome data somehow to decode errors. You just need that between your time boundaries to do it.
I guess what I wouldn't agree with that. I would say so the way I see it is suppose you have a big logical circuit already, it's all lattice surgery, every logical operation is order D. If you insert a transverse C naught in there without increasing the number of rounds, I think it'll still work.
Yeah, but it has a D round somewhere
It's okay,
to do error. It just needs some D round somehow. So like if you're just even demonstrating a single CMOS, if that's all you're demonstrating, you have to do D rounds around it to properly decode it. Otherwise, you're just decoding bell pairs and you'll never see it.
I see. So it's kind of like the setup of the experiment maybe didn't reflect. By the way, it sounds like we're shouting at each other.
It's a right. Well, I mean, it's a subtle point. I mean, the transverse of CNAP itself is depth 1. I fully agree with that. But if it is combined with faulty, well, that hardly has anything to do with the code state preparation. What does it really mean? Does that can we extrapolate that data to infer something about, oh, in my surface code architecture, transverse CNAP will perform this well? Can we say that?
I see. So they basically the residual noise in the system, that it's too small in there.
Right.
It would be larger if you had like 0 on preparations and 0 and then, and maybe it wouldn't be below the threshold.
Right.
I see. Okay, thanks.
Thanks. Awesome. Well, there's no more questions. Let's thank Jeongwan again.